In a lab under the border of France and Switzerland, a machine smashed 650 billion particles into each other, and one of them did not do what science said it must do. For 50 years, one theory predicted every particle we found before we found it. Physicists call it the Standard Model. It has never lost, until now. We are about to walk through a hidden force that may be bending reality, a ghost particle that could rewrite the family tree of matter, and a number climbing toward a threshold that has ended theories before. If you want more of this, hit subscribe. It helps more than you know. The countdown to that number has already started. Let's begin. Deep under the border of France and Switzerland, a particle called a B meson lived for less than a trillionth of a second. Then it fell apart. That should have been the end of the story. Trillions of particles die inside the Large Hadron Collider every single day, and almost every one of them follows the same script written decades ago. This one did not. Picture a machine shaped like a giant underground ring, 27 kilometers around, about the distance from one side of a big city to the other. Inside that ring, protons race in opposite directions at nearly the speed of light. When they slam together, the crash creates a storm of new particles, born and gone in an instant. Physicists built cameras the size of apartment buildings just to catch the wreckage. A B meson is one piece of that wreckage. It is made of two smaller particles called quarks, held together for a heartbeat before it breaks apart into something else. Scientists have watched this happen billions of times. They know the odds, they know the angles, they know exactly how often it should happen, and in what direction the pieces should fly. This time, the pieces flew wrong, not by a lot, not enough to make headlines on its own, but enough that a team of physicists at CERN, the European laboratory that runs the collider, stopped and looked twice. Then they looked 650 billion more times. That is not a typo. 650 billion B meson decays, recorded over 7 years, sorted, measured, and checked against the math. The math is called the Standard Model, and for 50 years it has never lost a fight. It predicted particles before anyone found them. It explained forces before anyone understood them. Scientists trust it the way a pilot trusts an altimeter. And on this one decay, in this one dark tunnel, the altimeter was lying. Here is what makes this stranger than every other false alarm before it. Two separate detectors, built by two separate teams, using two separate methods, caught the same disagreement. One is called LHCb, the other is called CMS. They were not looking for each other's mistakes. They found the same crack independently, like two witnesses describing the same car from two different street corners. Scientists have a way of measuring how surprised they should be. It is called a sigma. Low numbers mean coincidence. High numbers mean something real. This result landed at 4 sigma. That means the odds of this being random chance are about 1 in 16,000. Not proof, not yet, but close enough that some of the most cautious people in science are choosing their words very carefully. One physicist at the University of Edinburgh called it among the most significant results of the last few years at the collider. That is a loaded sentence from someone trained never to overstate anything. So what actually happened inside that tunnel? Why does a single meson, invisible to the naked eye, gone before you could blink, matter to anyone outside a physics lab? The answer has to do with a hidden kind of particle transformation that physicists nicknamed after a bird, a flightless one. And the shape of that transformation may be the first crack in the most successful theory human beings have ever built. We are just getting started. In 1977, a physicist named John Ellis lost a bet. As a joke, he had to work the word penguin into his next scientific paper. He found a way. He was describing a rare particle transformation, and when he sketched the path the particles took on paper, the loops and lines curled into something that looked, if you squinted, like a flightless bird standing on the ice. The name stuck. Nearly 50 years later, physicists still call it a penguin decay, and it just became the center of the biggest mystery in physics. Here is what actually happens. Deep inside a B meson sits a particle called a bottom quark. Left alone, quarks do not just transform into other quarks. The rules of the universe make that nearly impossible through the direct, simple path. So, the bottom quark cheats. It borrows energy for a fraction of an instant, conjuring invisible, short-lived particles that appear and vanish faster than light could cross a single atom. Physicists call this a quantum loop. Picture flipping a coin so fast it briefly exists as both heads and tails at once, then lands. That loop is the coin spinning in midair. Inside it, ghost particles come and go. A heavy particle called a W boson, another called a top quark, a Z boson, a flash of light called a photon. None of them stick around, but their fingerprints do. When the spin finishes, the bottom quark has transformed into a lighter cousin called a strange quark. Two more particles shoot out alongside it, a muon and its antimatter twin, the antimuon. Muons are heavier relatives of the electron, the same electron sitting in every atom in your body, just weighing about 200 times more. This is the penguin decay. It happens exactly the way the rulebook says an ordinary card trick should happen if the deck is fair. The standard model predicts with brutal precision how often this transformation should occur, and at what angles the muon and antimuon should fly apart afterward. The catch is that this decay is staggeringly rare. Out of every 1 billion B mesons, roughly one takes this path. Finding even a handful means sorting through mountains of ordinary, boring decays first. The way you would search a stadium crowd for one person wearing a specific shirt. That is exactly why physicists love it. A common event tells you what the universe usually does. A vanishingly rare one, born from a spinning loop of borrowed energy, is sensitive to things you cannot see any other way. If a hidden massive particle exists somewhere beyond our current detectors, too heavy for the collider to create directly, it can still slip into that spinning loop for an instant and leave a fingerprint on the outcome. Radioactivity itself was discovered this way. Scientists measured its effects 80 years before they ever directly saw the particle responsible. So when 650 billion of these penguin decays were finally tallied, added up, and compared against the prediction, physicists were not just checking a number, they were checking for a ghost, and the numbers came back wrong. Imagine counting every person on Earth 80 times over. That is roughly the number of B meson decays physicists sorted through to find this result. 650 billion collision events recorded between 2011 and 2018, sitting in digital storage across computing centers scattered around the world. Most of those decays were useless for this particular hunt. The team needed one specific transformation, a B meson breaking into a kaon, a lighter particle called a pion, and a pair of muons. Out of every million B mesons, only one takes this exact path. Finding it meant building machine learning software that could recognize the pattern automatically. The same kind of tool that recognizes a face in a crowded photograph, except the crowd was 650 billion particles deep, and the photograph was updating 1,000,000 times a second. Once they isolated enough of these rare events, the team measured two things: how often the decay happened and at what angles the resulting particles flew apart. The standard model makes a firm prediction for both. It is not a guess. It is a number calculated from the ground up, using the same equations that correctly predicted the mass of particles before those particles were ever detected. The angles came back skewed, not randomly scattered, the way a coin flip goes crooked by accident. Skewed in a consistent direction, over and over, across billions of repeated measurements. Physicists have been circling this exact discrepancy since 2013, when an earlier, smaller dataset first hinted at the same lopsided angles. Back then, the evidence sat around 3.7 sigma, intriguing but far from conclusive. Every year since, more data rolled in. The gap did not shrink the way a fluke should. It grew. By the time this newest analysis wrapped, the tension had climbed to 4 sigma. In plain terms, that means there is roughly a 1 in 16,000 chance the entire pattern is nothing but statistical noise, a coincidence born from counting enough particles that a strange pattern was bound to appear somewhere. 1 in 16,000 sounds small already. Compare it to something concrete. Your odds of being struck by lightning in a single year are roughly 1 in 500,000. This anomaly is over 30 times more likely to be real than a lightning strike is to hit you this year. And physicists do not even consider 4 sigma results proven yet. Their bar sits even higher. Here is the detail that turned heads across the entire field. A second detector, called CMS, built by an entirely separate team using different equipment and different methods, searched for the same decay independently. Its data was less precise, but it pointed in the exact same direction. 2 machines, 2 teams, 1 number, refusing to behave. The dataset used for this result closed in 2018. Since then, the upgraded collider has already gathered 3 times as much data, and it is sitting there right now, waiting to be analyzed. The next check is coming, and it will not leave much room for doubt either way. Before this crack appeared, the standard model had never truly lost. Not once in 50 straight years. Picture a rulebook that describes every known particle in the universe and every force except gravity, all wrapped into equations that fit onto a single T-shirt. That is the standard model. It was built piece by piece throughout the 20th century, and it has an almost unbelievable track record. It predicted particles before anyone ever saw them. The W boson, a particle that carries one of nature's fundamental forces, was written into the math years before any machine was powerful enough to create one. Scientists searched, and there it was, mass and all, matching the prediction almost exactly. The same happened with the Z boson. The same happened with the top quark, the heaviest quark ever found. The same happened, most famously, with the Higgs boson in 2012, a particle tied to why anything in the universe has mass at all. Predicted on paper decades before, it was caught inside this very collider. Score after score, test after test, the standard model kept winning. Even measurements that seemed to break the pattern eventually cracked under closer inspection instead. A few years ago, physicists thought they had caught a different particle, the W boson itself, sitting at the wrong mass. Excitement spread. Then more careful remeasurement came in, and the anomaly evaporated completely, gone, like it had never happened. That history is exactly why this new penguin decay result matters so much. Scientists are trained to be skeptical of their own excitement. They have watched dozens of promising anomalies fizzle out over the decades, undone by better data or a calculation error buried too deep to spot at first glance. A theory this successful earns the benefit of the doubt every single time. But here is what nobody can explain away this time. The standard model itself admits it is incomplete. It cannot explain gravity. It cannot explain dark matter, the invisible substance that outweighs all the visible stars and planets in the universe combined. It cannot explain why matter outnumbers antimatter, when the early universe should have created equal amounts of both. Physicists have always known this rulebook was missing pages. They just did not know where the missing pages would first show themselves. For half a century, every experiment confirmed the pages that were already written. This decay might be the first one pointing toward a page nobody has read yet. That is the tension sitting inside CERN right now. A theory with a perfect record, built by geniuses, tested relentlessly, staring down a stubborn number it cannot explain. Not a small deviation buried in noise. A pattern that keeps reappearing, tightening instead of fading, backed by 2 machines instead of 1. 50 years unbeaten does not mean unbeatable. It means whatever beats it will have to be extraordinary. Somewhere in your body right now, electrons are spinning around atoms, holding your cells together, letting your muscles fire and your thoughts flicker into being. An electron is one of the most familiar particles in existence. It also has a heavier twin almost nobody outside a physics classroom has heard of. It is called a muon. Picture the exact same particle, same charge, same basic behavior, just about 200 times heavier, like comparing a bicycle to a delivery truck built to the same blueprint. Muons do not stick around in ordinary matter. They live for about 2 millionths of a second before decaying away, raining down constantly from cosmic rays crashing into our atmosphere, or created briefly inside colliders like the one at CERN. Here is the rule that has stood since physicists first wrote the Standard Model. Electrons and muons are supposed to be interchangeable, at least when it comes to the fundamental forces of nature. If you swap an electron for a muon in a given process, the underlying physics should not care. The forces that push and pull on one should push and pull on the other with identical strength. Scientists call this idea lepton universality, and it has been tested again and again, holding firm nearly everywhere they looked. Nearly. Inside that penguin decay, the B meson can spit out either a pair of muons or a pair of electrons. If the rulebook is correct, both outcomes should happen at almost exactly the same rate once you account for the muon's extra mass. For years, LHCb measurements hinted that muons were showing up slightly less often than electrons in these rare decays. Not by a landslide, by a sliver, but a sliver that refused to disappear. Think of flipping two coins that are supposed to be perfectly identical over and over, millions of times, and one keeps landing on heads just a little more often than it should. A single strange run means nothing. A pattern that holds across billions of trials means something is different about the coins themselves. Earlier results along these exact lines eventually collapsed under more data. In 2022, a related measurement comparing electrons and muons in a different B meson decay evaporated once the full dataset came in, exactly like the W boson mass glitch before it. Physicists know this game well. Most flickers of new physics die quietly. This time, the flicker did not come from comparing electrons directly to muons. It came from the angles, the actual shape of the decay itself, deviating from prediction regardless of which lepton showed up. That distinction matters. It means this crack might be sturdier than the ones that came before it, rooted in the mechanics of the decay rather than a simple counting mismatch that better statistics could wash away. If electrons and muons really do respond differently to some hidden force, physicists would have to rewrite one of the deepest assumptions built into their entire rulebook. Twins that were never supposed to differ, quietly refusing to match. For years, this was a whisper buried in footnotes. Then it became a headline inside CERN itself. The moment came during a seminar, the kind of routine meeting where physicists present slides to colleagues who have seen 100 routine meetings before. This one was different. The LHCb collaboration stood up and presented their long-awaited results on the penguin decay, built from the full 7-year dataset, 650 billion decays deep. The room did not need dramatic music to understand what it was looking at. The angular measurements, the exact direction the muon pair flew apart from the kaon and pion, disagreed with the Standard Model prediction. Earlier versions of this same measurement, using smaller slices of data, had shown a similar gap sitting around 2.2 to 2.5 sigma. Interesting, but nowhere close to convincing. Skeptics in the room had every reason to expect this new, larger dataset to smooth the wrinkle out, the way better statistics usually do. Instead, the wrinkle held. Then it grew. What made this moment feel different from a decade of earlier false alarms was context nobody in that room could ignore. A separate, unrelated measurement, the muon's magnetic wobble, had been pointing in a similar direction for years, hinting that muons might behave slightly differently from what pure Standard Model math predicted. Now this penguin decay, built on a completely different process, involving completely different particles, was leaning the same way. Two independent puzzles, pointing at the same suspect. Physicists describe this feeling as coherence. A single strange number is easy to dismiss as noise. Multiple strange numbers, unconnected on paper, mysteriously aligned in the same direction, become much harder to wave away. It is the difference between one person claiming they saw something odd in the sky and 5 strangers on 5 different streets describing the identical shape. Inside that CERN seminar room, the mood shifted from routine to charged. Careers had been built cautiously around this exact number for over a decade. Scientists who chose to specialize in one of the rarest, hardest to measure decays in the entire field, betting that patience would eventually pay off. For the first time, patience looked like it might. Nobody popped champagne. Nobody claimed discovery. The standard model has survived worse scares before, and everyone in that room had lived through at least one anomaly that evaporated under closer study. But something had changed. The twins, electrons and muons, interchangeable for 50 years running, were behaving like they remembered which one was which. The next question was obvious, and it hung over the entire room. How sure can anyone actually be? The answer to that question has a name, a number physicists have used for decades to separate real discoveries from statistical ghosts. That number is called sigma, and understanding it is the only way to know how frightened or excited to actually be. 4 sigma. The phrase has been repeated throughout this story like a drumbeat. Here is what it actually means, and why physicists refuse to celebrate even though the number sounds enormous. Picture flipping a coin that should land heads exactly half the time. Flip it 10 times and get 7 heads, and nobody blinks. That happens by pure chance all the time. Flip it 1,000,000 times and get 700,000 heads, and something is clearly wrong with the coin. Sigma is the tool scientists use to tell the difference between an ordinary lucky streak and a coin that is actually broken. Each additional sigma represents another leap in confidence. 1 sigma might happen by accident, roughly 1 time out of 3. Nothing worth mentioning. 2 sigma narrows those odds down to about 1 in 20, the same rough threshold that gets a result written up in a lesser scientific journal, still not close to solid proof. 3 sigma tightens further, down to about 1 in 700, allowed to be called evidence, but still shaky ground to build a claim on. 4 sigma, where this penguin decay result now sits, corresponds to roughly a 1 in 16,000 chance that the entire pattern is a random fluke. To put that in a picture a stadium could hold, imagine filling 16,000 seats with people and telling them only 1 seat in the entire stadium holds the person responsible for a coincidence this specific. That sounds like overwhelming odds. It nearly is. But physics sets its bar for a confirmed discovery even higher than that. The reason traces back to hard lessons learned the hard way. Particle physics involves testing enormous numbers of different processes, angles, and combinations across enormous datasets. Test enough different things, and statistically, something is bound to look surprising purely by chance eventually. The same way flipping a coin 1,000,000,000 times guarantees a few unlikely streaks somewhere in the sequence, even with a perfectly fair coin. Scientists call this the look elsewhere effect, and it has burned careers before. So the field adopted an even stricter finish line, one final wall standing between an intriguing hint and an actual discovery. That wall sits far beyond where this result currently stands. 4 sigma earns respect. 4 sigma earns careful language, cautious optimism, and a green light to keep pouring resources into confirming it further. 4 sigma does not, on its own, earn a place in the textbooks. What earns that place is a single additional digit, 1 more sigma stacked on top of this one, and crossing that line requires something this entire field has been chasing for over a decade. More data than anyone has ever poured into this single, elusive, rare decay. That data already exists. It is sitting in storage right now, 3 times larger than what produced this result, waiting to be unlocked. 5 sigma. Physicists do not use this number casually. It is the line that separates a hint from history. At 5 sigma, the odds of an accidental fluke collapse to about 1 in 3.5 million. Stretch that into something you could actually picture. Imagine every single person living in a country the size of Ireland, and only one of them, somewhere in that entire population, holding the explanation for a coincidence this precise. That is the standard physicists demand before they will use the word discovery in an official sense. This threshold is not arbitrary caution dressed up as rigor. It exists because history taught this field a brutal lesson. Repeatedly, physicists have watched result after result look convincing at 3 sigma, only to quietly dissolve once more data arrived. The W boson mass anomaly looked shocking for years, discussed at conferences, debated in journals, until a more careful remeasurement made the entire discrepancy vanish. A related lepton comparison, hinting that electrons and muons behaved differently in a separate B meson decay, seemed rock solid in 2021 and evaporated completely by 2022. 5 sigma exists to prevent physicists from chasing ghosts. It forces patience onto a field built by people who, more than almost anyone, want to be the one who finds the crack that changes everything. That patience is being tested right now. The current penguin decay result sits at 4 sigma, a wall's height below the finish line, using data that was locked in back in 2018. Since then, the collider's upgraded detector, running in what scientists call Run 3, has already gathered roughly 3 times as many collision events. That new mountain of data is being processed as this very script reaches your ears. Here is the part that separates this moment from every previous false alarm in this exact story. The math on how much new data is needed to definitively cross the 5 sigma line has already been run. Physicists know, almost to the year, when this uncertainty will end. There will be no lingering decade of will it or won't it, the way earlier hints dragged on inconclusively for years at a time. The dataset already exists. The finish line is close enough to see. Add to that the deeper Run 4 upgrade planned for the 2030s, expected to multiply the total data collected by another factor of 15. If some hidden new particle really is bending this decay away from prediction, that mountain of future data will make the signal impossible to hide inside statistical noise any longer. If the anomaly holds, physicists will cross 5 sigma, and the standard model's 50-year winning streak will officially end, in public, on the record, with a discovery paper instead of a rumor. If the anomaly fades, the way so many before it have faded, this becomes one more entry on a long list of near misses, remembered fondly, taught to students as a lesson in humility. Either way, the wall is close now, and for the first time in this entire story, there is no more room left to hide. LHCb was not working alone. Buried in a different section of that same 27-kilometer tunnel sits an entirely separate detector, built by a different team, running its own independent hunt. Its name is CMS, short for Compact Muon Solenoid, and it caught something too. Picture 2 witnesses to the same accident, standing on opposite street corners, unable to see each other, giving their statements to police separately. If their stories line up on the small, specific details, the kind nobody would think to fake, that agreement carries far more weight than either statement alone. That is essentially what happened here. CMS was not specifically designed with this rare penguin decay as its primary focus, and its measurement of the process came back less precise than LHCb's dedicated, purpose-built analysis. But when CMS pointed its own instruments at the same decay and measured the same angles, its results leaned in the identical direction as LHCb's. Not the opposite direction, not scattered randomly. The same direction, the same deviation from the standard model's prediction. Physicists call this corroboration, and in a field littered with anomalies that vanished the moment a second team looked closely, corroboration from an entirely separate detector is rare enough to make even skeptics sit up. Consider what would have to go wrong for this to be a coincidence. LHCb and CMS use different detector designs, different software for reconstructing particle tracks, different calibration methods built by different engineering teams over different years. A mistake buried inside LHCb's specific software, a subtle bias in how it identifies muons, for example, would not necessarily show up inside CMS's completely different system. Two separate machines making the exact same undetected error, by pure chance, in the exact same direction, is its own kind of coincidence, layered on top of the original one. That does not make this anomaly proven. CMS's weaker precision means its result alone would never clear even the lowest bar for serious consideration. What it does is remove one of the easiest, most common explanations available whenever a lone experiment reports something strange, a hidden flaw specific to that one piece of hardware. Scientists have watched single detector glitches masquerade as groundbreaking discoveries before. A famous case involved a different experiment reporting particles that appeared to travel faster than light, a result that shattered headlines worldwide for weeks, until engineers traced the entire anomaly back to a loose fiber optic cable. One machine, one cable, one enormous false alarm. This time, the story running through two separate machines does not have an easy loose cable waiting to be found. Both detectors, independently built, independently calibrated, independently analyzed, are describing the identical crack in the same rulebook. Two witnesses telling the same story does not close the case. It does mean the case stays open, and it grows harder to explain away with each new machine that looks and sees the same thing. A single strange result invites doubt. Two independent machines agreeing invites something closer to dread, at least for physicists who have spent careers defending the Standard Model's perfect record. Here is the deeper reason this matters so much. Every layer of a particle physics experiment carries its own chance for error, stacked one on top of another like a tower of assumptions. The detector itself might have a flaw. The software reconstructing invisible particle tracks from raw electronic signals might carry a hidden bias. The statistical methods turning millions of collision events into a single clean number might be subtly miscalibrated in a way nobody has caught yet. Any one of these layers, quietly wrong, could produce a fake anomaly that looks completely convincing on paper. LHCb and CMS do not share these layers. They were built by different engineering teams, using different detector geometries, tuned with different calibration data, and analyzed using independently written software built by scientists who, in many cases, never spoke to each other while doing the work. That separation is not an accident. It exists specifically so that if two experiments ever do agree, physicists can trust the agreement means something real about the universe, rather than something shared about the equipment. Think of it like two separate labs testing a new medicine, using different patient groups, different hospitals, different doctors, never comparing notes until the very end. If both labs report the same surprising side effect, nobody assumes it is a coincidence of paperwork. Something about the medicine itself is doing this. That is roughly the position CERN sits in right now. Two experiments, unconnected at nearly every technical level, are reporting deviations from the same 50-year-old prediction, in the same specific decay, in the same direction. This is precisely why physicists reached for the word significant instead of staying silent, and precisely why particle physicists across the field, not just the two teams directly involved, began paying close attention. A flaw hiding inside one detector is a Tuesday. A flaw hiding inside two completely independent detectors, coincidentally producing the exact same skew, strains believability far more than the alternative explanation these scientists are now taking seriously. That something genuinely new is influencing this decay. None of this erases the need for caution. CMS's weaker precision means its agreement functions more like a supporting witness than a second conviction on its own. The full weight of this case still rests on LHCb's larger, more precise dataset, and on the future data still waiting to be analyzed. But the agreement between two separate machines has already done something quietly important. It has taken away the single easiest excuse available whenever an experiment reports something the textbooks did not expect. Nobody can point to one flawed cable, one buried software bug, one uncalibrated sensor, and make this entire story disappear. Two machines are watching the same crack, and neither one is blinking. Here is the strangest part of this entire mystery. The particle that might be causing all of this may never be directly created inside the collider at all. It could be too heavy, too fleeting, too far beyond what even the most powerful machine humans have ever built can produce head-on, and yet its fingerprints might already be sitting inside the data. This is possible because of that spinning quantum loop from earlier, the one where a bottom quark briefly borrows energy from nothing, conjuring a swirl of temporary particles before settling into its final form. Inside that loop, particles pop into existence and vanish again almost instantly, far too briefly to ever be captured directly by a detector. Physicists call these virtual particles borrowed from the universe on credit and repaid before anyone can catch them in the act. Picture flipping a coin so fast it briefly exists as a blur, neither fully heads nor fully tails, before it lands and reveals its final face. Everything that happens during that blur influences where the coin ultimately lands, even though nobody could freeze frame the blur itself. That blur is the quantum loop. The landed coin is the B meson's final decay. Under the standard model, that blur is populated by a known cast of characters: a W boson, a top quark, a photon, a Z boson, each one a well-understood, thoroughly tested particle. Together, their combined influence predicts exactly how the final decay should look, down to the angle the muon pair flies apart. But nothing rules out an additional guest slipping into that blur, one physicists have never directly detected, too heavy for the collider's raw collision energy to conjure on its own. Even a single extra ghost hiding inside that swirling loop, present for only a sliver of an instant, can shift the final outcome just enough to bend the angles away from prediction. The exact bending scientists have now measured across billions of decays. This is not a new trick in physics. It is one of the oldest, most reliable tools in the entire field. Radioactivity itself was measured, studied, and used for 80 years before anyone ever directly detected the W boson responsible for causing it. Scientists trusted the fingerprint long before they ever saw the hand that left it. That is exactly the position physicists find themselves in now. They are not staring at a new particle. They are staring at its shadow, cast backward through a spinning loop too fast for any camera, however advanced, to freeze. The question that follows is unavoidable. If something unseen really is hiding inside that blur, bending the outcome just enough to break 50 years of perfect prediction, what could it possibly be? Physicists already have two leading suspects in mind. One would rewrite the family tree of every particle in existence. The other would reveal an entire hidden force, sitting invisibly alongside the ones we already know. For over a century, physics has organized matter into two separate families that never mix. Quarks build protons and neutrons, the heavy stuff inside every atom's core. Leptons include electrons and muons, lighter particles that orbit around that core or drift freely through space. Two families, two sets of rules, never crossing paths directly. The leading suspect behind this entire anomaly is a hypothetical particle that would break that separation completely. Physicists call it a leptoquark, and the name says exactly what it does. It would act as a bridge, a single particle capable of connecting a quark directly to a lepton, something the current rulebook says should not exist at all. Picture two neighborhoods that have never once had a road connecting them, each with its own separate rules, separate customs, separate lives. A leptoquark would be the first bridge ever built between them, letting traffic flow directly from one side to the other for the first time in the history of the universe. If a leptoquark exists, it could slip into that spinning quantum loop inside the B meson's decay, alongside the familiar cast of W bosons and top quarks, and tug the outcome in a very specific direction. Crucially, it would not need to treat electrons and muons identically. A leptoquark could interact more strongly with one than the other, exactly the kind of imbalance physicists have been chasing since they first noticed muons behaving slightly differently from their lighter twin. This is not an idea invented last week to explain away an inconvenient result. Leptoquarks have circulated through theoretical physics literature for decades, originally proposed to explain deeper patterns in how particles are organized, long before anyone connected them to this specific B meson mystery. Multiple independent research groups have built detailed mathematical models showing that a leptoquark, tuned to the right mass and the right coupling strength, could account for this penguin decay anomaly and, remarkably, several other unrelated anomalies at the same time, including that lingering muon magnetic wobble mentioned earlier. One version of the idea goes even further, suggesting 3 separate leptoquark types might exist, one paired specifically with each type of lepton: an electroquark, a muoquark, and a tauquark, each acting as its own private bridge between the quark and lepton worlds. It sounds almost too tidy. That tidiness is exactly what makes some physicists cautiously excited and others deeply skeptical, since nature rarely hands over an explanation this clean without a catch buried somewhere inside it. No leptoquark has ever been directly observed. Powerful searches at the collider, aimed specifically at creating one head-on, have come back empty so far, which means if it exists, it must be heavier than current search limits allow, hiding just beyond the reach of a direct hit. That absence does not rule it out. It only means, if the leptoquark theory is correct, this penguin decay may be the closest humanity has ever come to it, catching its shadow through a spinning quantum loop instead of catching the particle itself. A bridge between 2 worlds that were never supposed to touch. And the first sign of it may already be sitting quietly inside 7 years of collision data. Stop and sit with the size of that idea for a moment. Quarks and leptons, treated as 2 entirely separate categories of matter since physicists first sorted them apart, might secretly be cousins, connected by a bridge nobody has ever directly seen. This is not a small housekeeping update to the rulebook. It touches something physicists call unification, the decades-old dream of finding a single deeper theory that explains all of nature's particles and forces as different faces of one underlying structure. History has already delivered pieces of this dream before. Electricity and magnetism looked like 2 completely unrelated forces for centuries, until a breakthrough in the 1800s revealed them as 2 expressions of the same underlying force, now called electromagnetism. Decades later, physicists discovered that electromagnetism and one of nature's other fundamental forces, the one governing radioactive decay, were secretly linked as well. Each time physicists found a hidden connection like this, it did not just tidy up the math, it revealed something true and previously invisible about how the universe is built underneath the surface. A leptoquark, if it turns out to be real, would be the next thread in that same long, unraveling story, tying quarks and leptons together after a century of treating them as permanent strangers. Some of the boldest theories go even further than a single leptoquark particle. A framework called Patti-Salam unification, proposed decades before this specific anomaly ever appeared, imagined an entire hidden symmetry where quarks and leptons start out as different versions of the exact same fundamental object, only appearing separate at the lower energies our universe currently sits at. Under this framework, leptoquarks are not a strange add-on bolted onto the existing rulebook. They fall out naturally, almost inevitably, from a deeper structure that was hiding underneath the standard model the entire time. If true, this would not just add one new particle to a chart on a classroom wall. It would suggest the entire chart was drawn with an artificial line down the middle, a line that never actually belonged there. There is a reason physicists have not simply declared this settled and moved on, despite how elegant the idea sounds. A leptoquark connecting quarks and leptons. This directly would also open the door to processes physics has never observed, and so far has very good reason to believe are essentially forbidden like a proton slowly disintegrating into lighter particles over unimaginable spans of time. Experiments have hunted for exactly this kind of proton decay for decades and found nothing, placing extremely tight constraints on how strong and how careful any leptoquark's connections would need to be to stay hidden from those searches while still explaining this anomaly. Threading that needle is possible on paper. Some of the more careful leptoquark models are built specifically to respect those constraints while still explaining the B-meson data. But it means this is not a free idea. It comes with a price tag, a long list of other experiments that have to remain silent for the theory to survive. A bridge between two ancient families of matter built narrow enough to explain one anomaly without accidentally letting through the one thing physics has never once observed. The leptoquark is not the only suspect. A second, equally serious candidate has its own name and its own strange implications. Physicists call it a Z-prime boson, and if it exists, it means an entirely new force has been quietly acting on the universe this whole time, hidden inside the forces we already thought we fully understood. Here is the shape of the idea. The standard model already includes a particle called the Z boson, a carrier of one of nature's four fundamental forces, the same family responsible for certain kinds of radioactive decay. A Z-prime boson would be a heavier cousin of that familiar particle, carrying a brand new force nobody has detected before, one that happens to interact differently with muons than it does with electrons. Picture radio stations. You already know the ones your favorite music plays on. A Z-prime would be an entirely new station, broadcasting on a frequency nobody has ever tuned into, invisible until someone happens to build a receiver capable of picking it up. If a Z-prime boson exists and interacts unevenly with electrons and muons, it could slip into that same spinning quantum loop inside the B-meson's decay, nudging the final angles away from the standard model's prediction in exactly the pattern physicists have now measured. Multiple theoretical groups have constructed detailed models showing a Z-prime, tuned to a specific mass and coupling strength, can account for this anomaly cleanly, in some cases even more cleanly than a leptoquark does. One especially elegant version of this idea ties the new force directly to the difference between muons and a third, even heavier lepton called the tau. Physicists gave this hidden symmetry a name built from that difference, and remarkably, models built around it do not just explain the B-meson anomaly. They can simultaneously help explain a completely separate mystery, the existence of dark matter, the invisible substance that makes up roughly 85% of all matter in the universe, gravitationally binding galaxies together despite emitting no light of its own. Stop and notice what just happened. A new force, invented specifically to explain one strange particle decay, might also help explain one of the largest unsolved mysteries in all of cosmology, almost as a side effect. That kind of overlap is exactly what makes theoretical physicists sit up. A theory built narrowly to patch one hole rarely helps with a completely unrelated one by accident. When it does, it is either an extraordinary coincidence or a genuine hint that the same missing piece explains more than one gap in the current picture at once. No Z-prime boson has ever been directly detected either. Just like the leptoquark, if it exists, it must be too heavy for the collider to conjure directly, its presence known only through the shadow it casts inside that spinning quantum loop. Two rival suspects, two very different explanations for the exact same crack, and only one of them can be right, if either is right at all. Physics has a habit of hunting for the theory that explains the most with the least. A single missing puzzle piece that, once found, snaps into place across several unrelated pictures at once, carries far more weight than a piece that only fixes one picture and nothing else. This is exactly why the Z-prime idea, and to a lesser extent the leptoquark idea, have generated so much excitement beyond just this one B-meson anomaly. Both candidates were originally proposed, in various forms, to address problems that had nothing directly to do with penguin decays at all. Consider the muon's magnetic wobble, mentioned earlier, as a separate, independent anomaly. Muons behave like tiny spinning magnets, and physicists can calculate, with extraordinary precision, exactly how much that spin should wobble under the influence of the Standard Model's known particles and forces. For years, actual measurements of that wobble came back slightly, consistently higher than the prediction allows. Just like the penguin decay, this discrepancy has hovered stubbornly for over a decade, refusing to fully resolve in either direction. A hidden Z-prime force, or a lepto-quark bridging quarks and leptons, could plausibly explain both anomalies simultaneously, using the exact same new particle, tuned to the exact same properties. That is a remarkable coincidence if these are two unrelated statistical flukes. It becomes something else entirely if they share a common cause. Then there is dark matter itself, perhaps the largest gap in modern physics. Every galaxy scientists have ever measured spins faster than the visible matter inside it should allow, as though an invisible scaffold of extra mass is holding everything together with additional gravity. Nobody has ever directly detected the particles responsible. Some Z-prime models, built around a hidden new force acting differently on muons than on other particles, naturally include a stable, invisible particle as part of their mathematical structure, a particle that behaves exactly like a dark matter candidate should. None of this proves anything on its own. Physicists have learned, through hard experience, that clever theories can always be built retroactively to explain whatever anomaly happens to be sitting on the table that year. The real test is whether a theory built to explain one thing makes clean, specific predictions about something else entirely, predictions that can later be checked independently. Some of these Z-prime and leptoquark models do exactly that. They predict specific, narrow mass ranges where new particles should eventually turn up in future collider searches. They predict specific patterns in other rare decays that have not yet been measured precisely enough to test. If those predictions come true in the coming years, it will look far less like coincidence and far more like discovery. For now, this remains a web of loosely connected threads, a penguin decay bending the wrong way, a muon wobbling slightly too much, a universe held together by mass nobody can see. Different observations, made by different teams, using different instruments, all circling the same missing piece. One hidden force, potentially explaining three separate mysteries at once. If physicists are right about that, the next several years are going to look very different from the last 50. Before this story goes any further, it deserves a dose of humility. This is not the first time physicists thought they had caught the Standard Model breaking. It might not even be the most dramatic false alarm in recent memory. A few years ago, an experiment called CDF at a different particle collider in the United States announced a result that stunned the entire field. They had remeasured the mass of the W boson, one of the most fundamental particles in all of physics, and found it noticeably heavier than the Standard Model predicted. The discrepancy was large. It was precise. It came from a well-respected team using over a decade of carefully analyzed data. For a while, this result was treated as one of the most serious cracks in the Standard Model ever reported. Theoretical physicists scrambled to explain it. Papers poured out, proposing new particles, new forces, new frameworks, all built to account for a W boson, stubbornly refusing to weigh what it should. Then other experiments checked the same measurement using their own independent data. One by one, they came back agreeing with the original Standard Model prediction instead of the surprising new result. The discrepancy, once treated as one of the most exciting anomalies in a generation, quietly dissolved. Most physicists now believe the original measurement contained a subtle, undetected error, somewhere deep inside its calibration, never fully identified, simply outvoted by better data from elsewhere. That story matters here for an uncomfortable reason. It proves that even a single team of skilled, careful, well-respected physicists, working with enormous datasets and rigorous statistical methods, can still produce a result that looks like a discovery and turns out to be a mistake instead. Confidence is not the same as correctness. A 4 sigma result, or even higher, has been wrong before. This is precisely why physicists studying this new penguin decay anomaly keep reaching for cautious language instead of triumphant headlines. They have lived through this exact emotional cycle already. The rising excitement followed by the quiet, deflating correction. Nobody wants to repeat it, especially not in public, especially not with a theory as important as the standard model on the line. So what makes this current anomaly different from that earlier false alarm? Independent corroboration from a second, completely separate detector, which the W boson case never fully achieved before it collapsed. A longer, more consistent history, with hints stretching back over a decade instead of appearing suddenly in one single measurement, and a direct, mechanical connection to at least one other lingering anomaly, the muon's magnetic wobble, rather than standing alone. None of that guarantees this result will survive, where the W boson mass glitch did not. It only means this particular crack has already cleared hurdles that earlier false alarms never managed to clear. The standard model has faced down imposters before and won every single time. The real test of whether this is finally different will not come from careful language or cautious optimism. It will come from data that is already sitting in storage, 3 times larger than what produced this result, waiting to be unlocked. Here is the detail that separates this anomaly from every ghost that came before it. It has already survived tests that killed off nearly every other exciting result in recent memory. Consider the timeline. This is not a single surprising measurement that appeared out of nowhere last year. Hints of something strange in this exact penguin decay first surfaced back in 2013, sitting around 3.7 sigma, intriguing but easily dismissed as a statistical fluke waiting to fade. Most anomalies at that early stage do exactly that. They fade. This one did not fade. Instead, as more data accumulated year after year, the discrepancy held its shape, then tightened. By the time the full 7-year dataset was finally analyzed in full, the tension had climbed to 4 sigma instead of collapsing back towards 0 the way random noise should. That pattern alone, an anomaly growing stronger rather than weaker as more evidence arrives, is itself statistically rare and difficult to produce by accident. Compare that trajectory to the W boson mass glitch from earlier, a result that appeared strong, confident, and precise the very first time it was measured, only to be directly contradicted once other experiments checked the same number independently. This penguin decay anomaly took the opposite path, growing more convincing over more than a decade of accumulating scrutiny rather than less. Then add the corroboration from CMS, an entirely separate detector, agreeing with the direction of the result despite using completely different hardware and completely different analysis methods. The W boson anomaly never received support like that from an independent machine before it fell apart. This one already has it. Layer on top of that the connection to the muon's magnetic wobble, an anomaly measured using an entirely different kind of experiment altogether, involving spinning particles in a magnetic field rather than colliding protons in a tunnel. 2 unrelated experimental setups, studying 2 unrelated physical processes, both hinting that muons interact with the universe slightly differently than the standard model predicts. That kind of overlap between fundamentally different types of experiments is exceptionally hard to fake through a shared hidden mistake. None of this makes the anomaly proven. Careful physicists studying this exact case have pointed out one legitimate remaining escape hatch, a specific, extremely difficult to calculate piece of the standard model's own math, nicknamed a charming penguin, involves quantum loops containing a particle called a charm quark, and these particular loops are notoriously hard to compute with full precision. If physicists have simply underestimated how much these charming penguin loops contribute naturally, without needing any new particle at all, some or all of this anomaly could theoretically dissolve through nothing more exotic than a math correction. Recent theoretical estimates studying this exact possibility conclude these charming penguin loops likely cannot account for the entire gap on their own, but likely is not certain, and this remains the single most serious mundane explanation still standing between this result and a genuine discovery. Everything now comes down to more data, sitting in storage, already 3 times larger than what built this result, with an even larger upgrade still to come. The anomaly has survived every test thrown at it so far. It has one wall left to climb. Step back from the collider for a moment and look up at the night sky. Every star you can see, every planet, every galaxy, every scrap of matter astronomers have ever photographed, adds up to only a small slice of what is actually out there. The rest, roughly 85% of all matter in the universe, is invisible. Physicists call it dark matter, and nobody has ever directly touched a single particle of it. Here is how they know it exists at all. Picture our solar system. The further a planet sits from the sun, the slower it moves. Uranus crawls through its orbit more than 4 times slower than Earth does, exactly as gravity's rules predict, because most of the mass pulling on every planet sits concentrated at the center, inside the sun itself. Galaxies should behave the same way. Stars near the crowded center should whip around fast. Stars out near the edges, far from most of the visible mass, should drift lazily, the way Uranus does. When astronomers actually measured this in galaxy after galaxy, the outer stars refused to slow down. They kept moving at nearly the same speed as stars much closer to the center, as if gravity itself did not care how far out you traveled. There is only one explanation that keeps standard gravity intact. Each galaxy must be wrapped in an enormous, invisible halo of extra mass, stretching far beyond where the visible stars end, pulling those outer stars along faster than the visible matter alone could ever manage. That invisible halo is dark matter, and it does not emit light, does not reflect light, does not interact with light at all. It only makes its presence known through gravity, tugging on everything around it while remaining completely unseen. This is not a fringe idea. It is one of the most tested, most confirmed patterns in modern astronomy, observed now in essentially every galaxy scientists have ever studied, including our own. Entire galaxy clusters show the same signature. The bending of light itself, as it passes massive clusters on its way to our telescopes, reveals the same invisible extra mass, warping space in ways only a hidden reservoir of matter could explain. And yet, after decades of dedicated searches, using detectors buried deep underground specifically to shield them from ordinary background noise, nobody has ever caught a single dark matter particle directly. Physicists know it is out there, shaping galaxies, holding the universe's largest structures together. They do not know what it actually is. This is where the story bends back toward that spinning quantum loop hiding inside a B meson's decay. Some of the exact same hidden particles proposed to explain the penguin decay anomaly, the Z-prime boson especially, carry mathematical fingerprints eerily similar to what a dark matter particle should look like. Stable, nearly invisible, interacting only faintly with the ordinary matter around it. A rare particle decay measured inside an underground tunnel in Europe might be circling the same missing piece as the galaxies spinning silently overhead. That connection is not proven yet, but it is exactly the kind of overlap that makes physicists stop treating this anomaly as an isolated curiosity and start wondering if it is a thread in something enormously larger. Here is the boldest possibility sitting on the table right now. This penguin decay anomaly might not just hint at a new particle. It might be the first indirect glimpse of dark matter itself, caught not by pointing a telescope at the sky, but by watching a B meson fall apart inside a tunnel under Switzerland. The logic works like this. Dark matter particles, whatever they actually are, must be almost completely invisible to ordinary matter, or astronomers would have detected them directly by now through countless dedicated experiments. But almost completely invisible is not the same as entirely disconnected. If dark matter particles share even the faintest connection to the particles inside a B meson, that connection could show up exactly where physicists have been looking all along, inside that spinning quantum loop where hidden, heavy particles leave fingerprints without ever being directly created. Several of the Z-prime boson models built to explain this anomaly include, almost as a built-in feature, a second, separate particle riding alongside the new force. That second particle behaves exactly the way theorists expect a dark matter particle to behave: stable, electrically neutral, barely interacting with anything except through this one narrow channel. In these models, the same hidden force twisting the B meson's decay angles could also be the very mechanism binding together every spinning galaxy in the visible universe. Picture it like discovering a single, faint radio signal, then realizing the same frequency, the same signature, also explains a strange pattern of static heard on the other side of the planet. Two mysteries, recorded on completely different instruments, suddenly reduced to one shared cause. This is not a settled conclusion. It is a hypothesis, one among several competing explanations still standing. Some leptoquark models explain the penguin decay without needing dark matter at all, treating this anomaly as a completely separate mystery from the galaxy rotation problem. Physicists genuinely do not yet know which path is correct, or whether either one is. But consider the size of what is being tested. If confirmed, this would mean a mystery astronomers have chased since the 1970s, watching galaxies spin in ways gravity alone cannot explain, and a mystery particle physicists have chased since 2013. Watching a rare decay bend in a direction the rulebook forbids are not two separate mysteries at all. They would be the same missing piece, observed from two entirely different angles, by two entirely different branches of physics that rarely cross paths. Nobody will know for certain until far more data comes in, both from the collider and from dedicated dark matter search experiments running in parallel around the world. But for the first time in years, physicists studying the sky and physicists studying subatomic decay are quietly circling the exact same suspect. A B meson, gone in a trillionth of a second, might be leaving fingerprints on the same invisible substance holding entire galaxies together. Dedicated dark matter detectors, buried deep underground in mines and tunnels specifically to block out interference, have spent years hunting directly for exactly this kind of particle, with no confirmed detection yet. A collider approaching the same target from a completely different direction, through a rare decay instead of a direct hit, offers a second path toward the same locked door. There is a particle spinning right now, inside a laboratory in the United States, behaving like a tiny magnet that refuses to follow the rulebook exactly the way it should. It is the same muon that keeps showing up throughout this story, and its stubborn wobble has been driving physicists half mad for over a decade. Here is the setup. A muon, like a spinning top, has a magnetic property physicists can calculate with staggering precision, incorporating the combined influence of every particle and force in the standard model, layered together into one single predicted number. Scientists built an experiment specifically to measure this wobble in real muons, spun around a giant magnetized ring, and compare the measured number against the prediction. For years, the measured number came back slightly higher than predicted, not by a landslide, by a sliver, the same kind of sliver that has haunted this entire story from the beginning. Run the experiment again, and the sliver held. Refine the calculation, and the sliver held. Build an entirely new, more precise version of the experiment, and the sliver held there too. This anomaly has nothing to do with B mesons on the surface. It uses a completely different experimental setup, a giant superconducting magnetic ring instead of a particle collider, measuring a completely different physical property. And yet it keeps pointing toward the exact same suspicion haunting the penguin decay result, that muons, the heavier cousin of the electron, might be interacting with some hidden force the standard model does not currently include. Physicists have spent years debating exactly how seriously to take this particular wobble, partly because the theoretical prediction itself has been unusually difficult to pin down, with different calculation methods producing slightly different target numbers to compare against. That theoretical uncertainty has kept this specific anomaly from ever reaching the kind of overwhelming statistical confidence the penguin decay result has now achieved. But here is why it still matters enormously to this larger story. Nearly every leading theory, proposed to explain the B meson anomaly, the leptoquark, the Z-prime boson, was originally built, at least in part, with this muon wobble already in mind. Theorists were not starting from scratch when this penguin decay result arrived. They already had a decade-old puzzle sitting on their desks, and suddenly a second, unrelated puzzle showed up speaking a strangely similar language. Two experiments, using two different machines, testing two different physical processes, both hinting that muons do not behave exactly the way 50 years of physics says they should. Coincidences like that do happen in science, but they happen far less often than skeptics would like. If a single hidden particle really is responsible for both anomalies at once, it would need to interact with muons in a very specific, very particular way, different from how it interacts with electrons. That detail alone would already start rewriting one of the deepest assumptions in the Standard Model. And it means whatever is bending that B meson's decay angles might already be leaving fingerprints somewhere else entirely, spinning quietly inside a magnet on the other side of the planet. A collider in Europe and a magnet in Illinois, built for different purposes by different teams, may have been quietly measuring the same ghost the entire time. Step back and count the threads gathered so far. A, B, meson, decaying at the wrong angle, measured by two independent collider detectors thousands of miles apart from each other in design philosophy despite sharing a tunnel. A muon wobbling slightly too much, measured by an entirely separate machine using an entirely separate method. A universe full of galaxies spinning faster than visible matter alone can explain, observed through telescopes rather than particle detectors at all. Three completely different fields of physics. Three completely different kinds of instruments. Three anomalies that, individually, would each earn a shrug and a note to keep watching. Together, they start to look like something else. Physicists have a name for this pattern. When scattered, unrelated observations begin leaning in a coordinated direction. They call it convergent evidence, and it carries far more weight in science than any single result ever could on its own, no matter how statistically significant that single result looks in isolation. Here is why convergence matters so much. A mistake hiding inside one experiment is common. A calibration error, a software bug, a subtle bias in how particles are identified. These things happen constantly in cutting-edge science, and skilled scientists catch most of them before publication. But a mistake capable of producing the exact same false signal, independently, inside three unrelated experiments, built by three unrelated teams, using three fundamentally different kinds of instruments, becomes almost impossible to imagine by pure chance. Think of it like three separate security cameras, positioned at different angles around a building, none of them able to see each other, none of them synced together, all three independently recording the same unexpected figure, crossing the same courtyard at the same time. One blurry camera might be a glitch. Three cameras, agreeing on the shape, the direction, and the timing, stop looking like a glitch and start looking like evidence. This does not mean physicists have found the culprit yet. Nobody has directly detected a leptoquark. Nobody has directly detected a Z-prime boson. Nobody has directly detected a dark matter particle. The convergence lies entirely in the shadows these hypothetical particles would cast, not in the particles themselves, but shadows pointing the same direction from three unrelated sources are exactly how physics has cracked open its biggest mysteries before. Astronomers first suspected dark matter existed purely from mismatched shadows, like these gravitational fingerprints with no visible source, decades before any dedicated search experiment ever attempted to catch a particle directly. The shadow came first. The hunt for the source came after. That is roughly where this story sits right now. Three shadows, cast by an unseen hand, stretching across three completely different corners of physics. Whatever is casting them has not shown its face yet, but it is getting harder, chapter by chapter, experiment by experiment, for that hand to stay hidden much longer. Scientists working in each of these three fields rarely cross paths day to day, publishing in different journals, attending different conferences, trained in different specialties. That this pattern still managed to surface across all three anyway says something about how strong the underlying signal may actually be, cutting through the normal walls that usually separate one branch of physics from another. Every uncertainty in this story has an expiration date, and physicists already know roughly when it arrives. The dataset behind the current 4 sigma result closed back in 2018. Since then, the upgraded collider has kept running, kept smashing protons together, kept recording collision after collision inside a completely rebuilt version of the LHCb detector. This new era carries its own name inside the physics community. They call it Run 3, and it has already gathered roughly 3 times as many collision events as the entire dataset used to produce this current anomaly. That mountain of fresh data exists right now, sitting in storage, waiting for the same kind of careful, painstaking analysis that took the original team years to complete the first time around. Picture rerunning an experiment you have already run once, except this time you have 3 times the raw material to work with, using detector upgrades built specifically to catch rare events like this penguin decay with even greater precision than before. The improved LHCb detector, switched on in 2022, was engineered in part with exactly this kind of rare decay measurement in mind, a direct response to the tantalizing hints that had already been accumulating for nearly a decade by that point. Physicists have already calculated, with reasonable confidence, how much additional data is required to push this result decisively past the 5 sigma discovery threshold, assuming the underlying anomaly is real and does not fade the way so many earlier hints have faded before it. That calculation gives this story something rare, an actual, foreseeable ending, rather than the open-ended uncertainty that dragged on for over a decade during the anomaly's earlier, weaker years. This stands in sharp contrast to how these things usually unfold. The muon wobble anomaly has lingered for over 10 years without fully resolving, partly because theoretical predictions themselves remain genuinely difficult to pin down with total confidence. This penguin decay story does not carry that same lingering uncertainty. The math is comparatively cleaner. The path forward is comparatively clear. More data, processed and compared against prediction, will either push the anomaly past the discovery line or shrink it back down towards statistical noise. There is no guarantee which way it goes. History, especially the collapsed W boson mass anomaly, has taught physicists not to assume a promising 4 sigma result is destined to become a confirmed 5 sigma discovery. Plenty of exciting hints have shrunk instead of grown once fresh data finally arrived. But unlike almost every previous chapter of this exact scientific mystery, nobody has to wait for a lucky future breakthrough or an unplanned new measurement. The instrument that will settle this question already exists. The data it needs is already flowing in. Physicists across the world are simply waiting for the analysis to finish, running the same rigorous checks that took years the first time, hoping the answer arrives faster now that the entire process is better understood. The race has already started. Nobody outside the collaboration knows exactly how it ends yet. But for the first time in this entire story, everyone agrees on when the finish line will finally come into view. For 13 years, the finish line kept moving. It has finally stopped moving, and it is now close enough to see, beyond the current Run 3 data already flowing in, an even larger transformation is scheduled for the 2030s, one that could turn this lingering 4 sigma hint into either the most important physics discovery in half a century or the most thoroughly buried false alarm in the field's entire history. Engineers are already planning a major upgrade to the Large Hadron Collider itself, designed specifically to dramatically increase how many proton collisions the machine can produce and record every single second. Once complete, this upgrade is expected to eventually deliver a dataset roughly 15 times larger than the one used to produce this current result. An almost unimaginable mountain of B-meson decays stacked on top of everything already collected. Picture the original 650 billion decay analysis as a single glass of water pulled from an ocean. Run 3, already 3 times larger, becomes 3 glasses. This future upgrade, 15 times beyond even that combined total, becomes something closer to an entire swimming pool, all pulled from the exact same ocean of raw collision data, searching for the exact same rare, elusive signal. At that scale, statistical noise has essentially nowhere left to hide. If this anomaly is nothing more than an unlucky coincidence, an unusual but ultimately random cluster of decays that happen to skew in one direction by chance, a dataset this enormous will wash that coincidence away completely. The way pouring an entire ocean through a filter eventually reveals whether a single suspicious grain of sand was ever really there at all. If the anomaly is real, this same flood of data becomes the tool that finally proves it beyond reasonable doubt, likely pushing the statistical significance far past the 5 sigma discovery threshold, potentially high enough to start directly measuring the properties of whatever hidden particle is actually responsible, rather than just detecting its shadow. This is the part of the story where science moves from indirect fingerprints toward direct confirmation. Right now, physicists are inferring the possible existence of a leptoquark or Z-prime boson purely through subtle shifts in decay angles, shadows cast by something too heavy and too fleeting to catch directly. With enough additional data, and eventually with higher energy collisions from future upgraded runs, physicists may finally gather enough evidence to pin down the actual mass of whatever particle is responsible, narrowing the search enough that a future, even more powerful collider could attempt to create it directly instead of merely detecting its influence from a distance. None of this happens quickly. These upgrades unfold over years, sometimes over an entire decade, built by international teams coordinating across dozens of countries and thousands of scientists and engineers. Patience remains the only option available, but for a mystery that began as a single, easily dismissed footnote back in 2013, arriving at a scheduled, foreseeable, and overwhelming final verdict feels almost unprecedented. 15 times more data stands between physics and an answer it has been chasing, in one form or another, for well over a decade. 15 times sounds abstract until you picture it as 15 separate versions of this exact same 7-year hunt, compressed into one dataset, all searching for the same single number. Imagine, for a moment, that the anomaly holds. Imagine the extra data arrives, the significance crosses 5 sigma, and CERN officially announces that the standard model has been broken for the first time in 50 years. What actually changes? The honest answer is both less dramatic and more profound than most people expect. Your phone still works tomorrow morning. Gravity still holds you to the ground. Nothing about ordinary daily life shifts overnight, because whatever new particle or force is responsible for this anomaly acts only under extraordinarily rare, extraordinarily specific conditions, the kind that only show up once in every billion B-meson decays inside a machine built specifically to hunt for exactly this kind of needle in an impossibly large haystack. What changes is the map. For 50 years, physicists have used the standard model as the outer boundary of known reality, the edge past which textbooks simply wrote unknown and moved on. A confirmed discovery here would not erase that map. It would extend it, adding new territory that had never officially existed before, forcing an entire generation of physics textbooks to include a new particle or an entire new force, standing alongside gravity, electromagnetism, and the 2 nuclear forces that have anchored physics classrooms for generations. Consider how the last time this happened reshaped the field. When the Higgs boson was finally confirmed in 2012, it did not rewrite everyday life either. It confirmed the final missing piece of a puzzle theorists had already mostly assembled decades earlier on paper, explaining why particles have mass at all. That confirmation did not change how your car engine works. It changed how deeply physicists understood the universe underneath that engine, closing one enormous open question while immediately opening several new ones about what lies beyond it. A confirmed leptoquark or Z-prime boson would do something even larger. Rather than completing the existing standard model the way the Higgs boson did, it would prove the standard model was never the complete final answer to begin with, exactly as physicists have suspected for decades, given the theory's inability to explain gravity, dark matter, or the imbalance between matter and antimatter. It would be the first direct, laboratory-confirmed crack in that foundation, rather than a philosophical argument about the theory's known limitations. That crack would immediately reshape where billions of dollars in future research funding gets directed. It would validate specific theoretical frameworks that have been developed for decades without any experimental confirmation, while ruling out competing frameworks that predicted a different outcome entirely. It would give the next generation of even more powerful colliders, still being planned and debated today, a specific, concrete target to search for directly, rather than a vague hope of finding something new. Perhaps most importantly, it would prove something bigger than any single particle. It would prove that after 50 years of an unbroken winning streak, careful, patient, decade-spanning science can still crack open the universe's deepest remaining secrets, hiding in plain sight inside a decay so rare it only happens once in every billion attempts. The map would still show mostly familiar territory, but for the first time in 50 years, one small corner of it would finally be redrawn. Physics has watched a dominant theory collapse before. It happened just over a century ago, and the story of how it unfolded offers a useful preview of what might be coming. For over 200 years, Isaac Newton's laws of motion and gravity reigned as the undisputed foundation of physics. Newton's equations predicted planetary orbits with extraordinary precision. They explained falling apples, swinging pendulums, and cannonball trajectories with a level of accuracy that made the entire framework feel less like a human invention and more like an unshakable law of nature itself. Then a small, stubborn anomaly appeared. The planet Mercury's orbit around the Sun did not behave exactly the way Newton's equations predicted. The mismatch was tiny, a barely noticeable drift in the precise direction Mercury's orbit slowly rotated over time, something almost nobody outside professional astronomy would have ever noticed on their own. For decades, scientists assumed some undiscovered planet, tucked in close to the Sun, was tugging on Mercury and causing the extra drift, the same way an unseen planet named Neptune had previously been discovered by exactly this kind of gravitational detective work. No such planet was ever found. The tiny mismatch simply persisted, stubbornly, refusing every explanation offered within Newton's existing framework. Then Albert Einstein published general relativity in 1915, an entirely new way of understanding gravity itself, describing it not as a simple force, but as the bending of space and time around massive objects. Almost immediately, Einstein's new equations explained Mercury's stubborn orbital drift perfectly, without needing any hidden extra planet at all. Newton's rules were not thrown away entirely. They still work beautifully for nearly every everyday situation, from throwing a baseball to launching a rocket. But they turned out to be an approximation, extremely accurate under most conditions, breaking down only in the most extreme situations, close to enormous gravitational fields where Einstein's deeper framework was needed instead. Notice the shape of that story. A theory considered essentially perfect for 2 centuries, a tiny, persistent anomaly nobody could initially explain away. Years of searching for a mundane, boring explanation within the existing rules, and eventually, a breakthrough that did not simply patch the old theory, but revealed it as one special case inside something larger and stranger. This penguin decay anomaly may be following the exact same pattern, just written in an entirely different chapter of physics, using particle decays instead of planetary orbits. A persistent, small mismatch, years spent hunting for a mundane explanation, and now, a real possibility that whatever comes next will not simply patch the standard model, but reveal it as one special case inside something larger, still waiting to be fully understood. Mercury's drift took decades to fully resolve after Einstein's breakthrough, as scientists tested and confirmed general relativity's predictions again and again. If history repeats itself here, confirming and fully understanding whatever lies behind this new anomaly could take just as long. There is one meaningful difference worth noting. Einstein's breakthrough arrived as a single, sweeping new theory, developed largely by one mind working through the mathematics alone. Whatever eventually explains this B-meson anomaly will more likely emerge the way most modern physics does now. Built collaboratively across dozens of research groups, tested piece by piece, refined through argument and counter-argument until only the strongest explanation survives. Here is a question that has haunted physicists since the earliest moments of the universe were first understood mathematically. When the universe began, physics says it should have created matter and antimatter in exactly equal amounts. Antimatter behaves almost identically to ordinary matter, same mass, opposite electric charge, except when matter and antimatter ever meet, they annihilate each other completely, converting entirely into pure energy. If the early universe truly created equal amounts of both, everything should have annihilated itself almost instantly, leaving behind nothing but a universe filled with light and radiation, devoid of any solid matter at all. No stars, no planets, no B-mesons decaying inside underground tunnels, no physicists to measure them. Obviously, that is not what happened. You exist. Stars exist. Something tipped the early universe's balance ever so slightly toward matter over antimatter, leaving behind a tiny leftover surplus once the annihilation finished. A surplus that eventually grew into every star, planet, and living thing that has ever existed. Physicists call this imbalance baryon asymmetry, and explaining exactly why it happened remains one of the largest unsolved mysteries the standard model cannot fully account for on its own. This is where B-mesons re-enter the story from an entirely different angle. These same particles, sitting at the center of the penguin decay anomaly, have already proven capable of behaving slightly differently from their antimatter counterparts under certain conditions. A subtle asymmetry physicists first confirmed decades ago studying a closely related particle. That asymmetry was an important clue, but nowhere near large enough on its own to explain how the entire universe ended up tilted so heavily toward matter. Physicists have long suspected that additional, undiscovered particles or forces might be needed to fully explain the imbalance, contributing extra asymmetry beyond what the standard model alone can account for. A new leptoquark, or a new Z-prime boson, of exactly the kind currently being proposed to explain this penguin decay anomaly, could plausibly contribute additional pieces to that same unsolved puzzle, depending on its exact properties. This connection remains far more speculative than the dark matter link explored earlier. No current theoretical model directly ties this specific anomaly to a complete explanation of the universe's entire matter-antimatter imbalance. But the particles at the center of this story, B-mesons built from quarks that transform through matter and antimatter pathways alike, sit exactly in the kind of experimental territory where physicists expect answers to this deeper question might eventually be found. Every existing star, every planet, every person who has ever lived exists only because of an imbalance physics still cannot fully explain. A rare, stubborn decay, refusing to match 50 years of prediction, might be circling closer to that answer than anyone initially expected when this entire story began with a single strange number back in 2013. Physicists sometimes describe this imbalance as the reason anything is here to ask questions at all. Without it, no telescopes, no underground tunnels, no scientists standing in a seminar room comparing 650 billion decays against a prediction. Just an empty universe of light, with nobody left to notice the silence. Before getting too far ahead of the evidence, this story deserves an honest visit to the graveyard. Physicists have proposed dozens of grand replacement theories for the Standard Model over the decades, most of them built with genuine mathematical elegance, and most of them have not survived contact with experimental reality. Consider supersymmetry, once considered the most promising extension to the Standard Model available. The theory proposed that every known particle has an undiscovered, heavier partner particle, a parallel set of matter that could elegantly solve several deep theoretical problems at once, including offering a natural, built-in candidate for dark matter. For decades, supersymmetry dominated theoretical physics conferences, inspired thousands of research papers, and generated enormous excitement about what the Large Hadron Collider might eventually discover once it reached high enough collision energies. The collider reached those energies. The predicted supersymmetric partner particles never showed up. Search after search came back empty, pushing the possible mass of these hypothetical particles higher and higher, past where the theory's most elegant, natural versions could still comfortably explain what physicists were originally hoping to explain. Supersymmetry has not been completely ruled out entirely. More complicated and less elegant versions can still technically survive current search limits, but the theory's golden era of confident predictions has largely passed. String theory tells a similar cautionary story from an even more ambitious angle, attempting to unify all fundamental forces, including gravity itself, into a single elegant mathematical framework built from tiny vibrating strings instead of point particles. Decades of intense theoretical work have produced extraordinary mathematics, but the theory has struggled to make specific, testable predictions that any current or near-future experiment could actually check, leaving it largely outside the reach of direct experimental confirmation so far. This graveyard exists for an important reason worth remembering here. Building an elegant, mathematically beautiful theory is far easier than building one nature actually chose to use. Physics history is littered with beautiful ideas that turned out to simply be wrong, or at least not yet supported by any real evidence. This matters directly for the leptoquark and Z-prime theories currently being discussed to explain the penguin decay anomaly. Both ideas are elegant. Both ideas connect multiple separate mysteries together in satisfying ways. Neither idea has been directly confirmed by any experiment yet, and both remain vulnerable to the exact same fate that eventually caught up with supersymmetry's most hopeful early predictions. The difference this time is the nature of the evidence already in hand. Supersymmetry was largely a theoretical prediction, searching for experimental confirmation that never fully arrived. This anomaly began with the experimental evidence itself, a real, measured deviation from prediction, with theorists scrambling afterward to explain what might be causing it. That order matters. It does not guarantee success where supersymmetry has largely stalled, but it means this story is not simply another beautiful idea waiting hopefully for confirmation. It is a confirmed anomaly waiting for its explanation to be properly identified. The graveyard is full of theories nature never chose to use. This time, nature moved first, and the theories are still racing to catch up. There is a pattern buried inside particle physics history that deserves its own honest chapter. Most exciting anomalies, the overwhelming majority of them, quietly die within about 10 years of first appearing. Understanding why makes it easier to judge whether this particular anomaly deserves to be treated any differently. Anomalies typically emerge the same way this one did, as a modest statistical wrinkle, sitting somewhere between 2 and 3 sigma, intriguing enough to publish, nowhere near strong enough to draw any firm conclusion. From that starting point, one of two things eventually happens as more data accumulates. Either the wrinkle grows stronger, tightening toward higher significance the way a real physical effect should behave under closer scrutiny, or it slowly fades back towards zero, revealing itself as nothing more than an unlucky statistical fluctuation. the kind that will always occasionally appear somewhere across the vast number of measurements particle physicists constantly perform. The overwhelming majority fade. This happens for straightforward, well-understood reasons. Early measurements often rely on smaller datasets, more vulnerable to random statistical noise, skewing results in one direction purely by chance. Early calibration methods are less refined than the sophisticated techniques developed later once a full decade of scientific scrutiny has had time to catch and correct subtle systematic errors. And scientists, being human, sometimes unconsciously favor analysis choices that make an exciting early result look slightly stronger than a fully neutral analysis would have shown, an effect statisticians call confirmation bias, one that tends to naturally wash out once independent teams repeat the measurement using their own separate methods. This penguin decay anomaly has already outlived that typical 10-year expiration window. Its earliest hints surfaced back in 2013. 13 years have now passed. Rather than fading the way the statistical odds suggested it eventually should, the anomaly has done the opposite, growing from an early 3.7 sigma hint into today's 4 sigma result, gaining independent corroboration from a completely separate detector along the way. That trajectory alone does not guarantee this anomaly belongs in the small surviving minority rather than the much larger graveyard of forgotten false alarms. Even genuinely rare statistical flukes occasionally happen to grow stronger before eventually collapsing, purely by chance, the same way an unusually long winning streak at a casino can persist for an uncomfortably long time before the odds inevitably catch up. But every additional year this anomaly survives, every additional independent measurement that corroborates, rather than contradicts it, shifts the probability further away from coincidence and further towards something real. 13 years is already an unusually long survival time for any particle physics anomaly. The data currently being processed right now, 3 times larger than everything that came before it, will very likely settle the question for good, one way or the other, within the next few years. Veteran physicists sometimes joke that the graveyard of dead anomalies is the busiest place in the entire field, filled with results that once dominated conference talks before quietly vanishing from the conversation within a few years. Whatever emerges from this particular anomaly, it has already spent longer in the spotlight than most of its neighbors in that graveyard ever managed. Behind every measurement in this story sit real scientists who chose, often early in their careers, to specialize in one of the hardest, rarest, most technically demanding corners of particle physics available. Studying penguin decays is not a fast path to easy publications. It requires sorting through hundreds of billions of ordinary events just to isolate a handful of the specific transformation being studied, then spending years refining statistical methods precise enough to trust the result. Physicists who chose this path decades ago were making a quiet bet. They were betting that patience, technical rigor, and years of unglamorous, detailed work would eventually pay off, even without any guarantee the anomaly they were chasing would ever amount to anything more than a footnote in an eventually forgotten paper. For over a decade, that bet looked uncertain at best. Early hints hovered around statistical significance, too weak to build a confident career narrative around. Colleagues studying flashier, more headline-friendly corners of physics moved faster toward publications and recognition. The scientists dedicated to this particular decay kept measuring, kept refining, kept publishing incremental updates that rarely made headlines outside specialized physics journals. One physicist at the University of Edinburgh, who has spent significant portions of his career on exactly this measurement, described this newest result as among the most significant findings the collider has produced in years. That kind of statement, from someone who has spent over a decade in the technical trenches of exactly this specific decay, carries different weight than excitement from an outside observer with no direct stake in the outcome. This human dimension matters for understanding how science actually works, beyond the equations and statistical thresholds. Major discoveries rarely arrive as sudden lightning bolts. They arrive after decades of patient, often thankless work by scientists willing to spend entire careers chasing a single stubborn number, uncertain until the very end whether their years of effort would culminate in a landmark discovery or quietly fade into the long list of forgotten anomalies. If this result eventually crosses the 5 sigma threshold, the scientists who spent their careers on this specific decay will have made one of the more consequential bets in modern physics, choosing years ago to dedicate themselves to a measurement most of the field considered a long shot at best. If the anomaly instead fades the way so many before it have faded, those same scientists will still have contributed something valuable, ruling out an important possibility and sharpening the tools future physicists will use to hunt for the next promising crack in the rulebook. Either outcome represents real scientific value, even though only one path leads to headlines. That distinction rarely gets mentioned outside physics departments, but it sits quietly underneath every number, every sigma, and every careful sentence found throughout this entire story. Somewhere right now, a graduate student is being trained on exactly this kind of measurement, learning the same painstaking techniques that built this anomaly in the first place. Unaware, yet, whether their own career will end up chasing a landmark discovery or quietly closing off one more possibility for the scientists who come after them. Imagine the specific moment this anomaly finally crosses the 5 sigma threshold, assuming it eventually does. What actually happens inside CERN in the hours and days immediately following that announcement? The scientific process itself would not stop or slow down. Crossing 5 sigma would not immediately reveal which specific theory, a leptoquark, a Z-prime boson, or something else entirely unexpected, actually explains the anomaly. It would simply confirm, beyond any reasonable statistical doubt, that something real and currently unexplained by the standard model is genuinely influencing this decay. The deeper hunt for the exact identity of whatever is responsible would only be beginning. Almost immediately, theoretical physicists around the world would begin comparing the newly confirmed, more precise measurements against every existing leptoquark and Z-prime model already built over the preceding years, checking which specific version, tuned to which specific mass and coupling strength, best matches the newly available data. Models that fail to match would be discarded. Models that succeed would gain enormous new attention and funding, guiding where future search efforts should focus their limited resources. Simultaneously, engineers and physicists operating other experiments around the world and other detectors within the collider itself would immediately begin searching more aggressively for direct evidence of the responsible particle, rather than merely its indirect shadow. If a specific mass range becomes newly favored by the confirmed anomaly, dedicated search efforts would concentrate specifically within that narrowed window, dramatically increasing the odds of eventually creating and directly detecting the particle itself, rather than continuing to infer its existence purely through indirect effects. Funding conversations would shift as well, though more gradually than headlines might suggest. A confirmed discovery this significant would strengthen the case for future, even more powerful collider projects currently being debated and planned, giving those enormously expensive, decade-spanning projects a concrete, confirmed target to search for, rather than a more speculative, open-ended mission statement. And within the broader scientific community, something more difficult to quantify would shift as well. An entire generation of physicists who have spent their careers operating entirely within the boundaries of the standard model would suddenly find themselves working at the edge of confirmed new territory, the first such territory discovered in this way in decades. Physics textbooks, physics curricula, and the entire framework taught to the next generation of students would eventually need updating, incorporating a discovery that had been rumored, debated, and cautiously anticipated for well over a decade before finally becoming official. None of this would happen instantly or dramatically. Science rarely announces itself with fireworks. It would unfold through careful papers, cautious conference presentations, and years of follow-up work, the same patient, methodical process that built this entire anomaly in the first place, one careful measurement at a time. The public announcement itself would likely arrive as a single, understated sentence buried inside a much longer, technical presentation, the way the Higgs boson discovery was first unveiled. Only later, once the wider world caught up with what had actually happened, would the true scale of the moment become clear to anyone standing outside the physics community itself. Step back now, all the way back, and look at the full shape of what this single, rare particle decay is actually asking. It is not simply asking whether one new particle exists somewhere in the universe. It is quietly asking whether the entire chart of known particles, the one taught in every introductory physics classroom around the world, was ever actually complete to begin with. Every particle currently known, every quark, every lepton, every force-carrying boson, fits neatly into a specific, organized structure physicists finalized decades ago. That structure explained everything scientists could measure at the time, and it has continued explaining everything measured since, with remarkable, unbroken precision for 50 consecutive years. If a leptoquark exists, that entire chart requires a fundamentally new category, an entirely new type of connection between particle families that were previously assumed to be permanently, structurally separate from one another. If a Z-prime boson exists, the chart requires an entirely new force, standing alongside gravity and electromagnetism as a fifth fundamental interaction shaping the universe, hidden in plain sight for the entire history of modern physics, because it only reveals itself under extraordinarily rare, extraordinarily specific conditions. Either possibility does not simply add one new entry to an existing list. It suggests the entire existing list was always secretly smaller than reality itself, a limited, incomplete snapshot of something significantly larger, still waiting to be properly mapped out. Every particle currently known would remain exactly as real and as important as before, but each one would need to be understood as a piece belonging to a larger, previously invisible structure. The way stars in the night sky remained exactly the same stars, yet transformed entirely in meaning once astronomers realized they belonged to an enormous galaxy, rather than existing as scattered points of light with no larger relationship connecting them. This is the deepest reason this single anomaly has captured such intense attention across the entire field of physics, far beyond the specific handful of scientists directly studying B mesons. It is not really a story about one rare particle decay. It is a story about whether human beings have finally mapped the entire structure of matter and force, or whether an enormous, previously unseen wing of that structure has been sitting quietly undiscovered this entire time, waiting for the right rare decay, inside the right underground tunnel, to finally reveal its presence. 50 years of unbroken success convinced an entire generation of physicists they were close to a complete picture. A single B meson, breaking apart at a slightly wrong angle, 650 billion times in a row, is now asking that generation to consider they might have only been looking at part of the painting all along. Every earlier expansion of that painting, from the discovery of the neutron to the confirmation of the Higgs boson, felt impossible, right up until the moment it was confirmed. There is no reason to assume this next expansion, if it comes, will feel any less startling to the physicists who have spent their careers memorizing the painting as it currently stands. There remains a very real possibility, one worth sitting with honestly, that all of this eventually amounts to nothing. The additional data arrives, the significance shifts, and the anomaly quietly fades back toward the Standard Model's original prediction, joining the long list of promising cracks that ultimately turned out to be nothing more than statistical noise or an underestimated calculation. This outcome would not represent a failure of science. It would represent science working exactly the way it is designed to work, patiently testing every promising anomaly against overwhelming amounts of additional evidence, refusing to declare victory until the evidence becomes truly undeniable. The W boson mass glitch collapsed this same way. So did an earlier, closely related B meson measurement back in 2022. Both collapses strengthened physics rather than weakening it, sharpening exactly how confident scientists should be before trusting any future anomaly of similar size. And yet, this particular outcome unsettles some physicists more than a straightforward confirmed discovery would. Here is the uncomfortable reason why. If this anomaly, which has already survived 13 years of increasingly rigorous scrutiny, corroboration from a second independent detector, and a mechanically plausible connection to at least one other unrelated anomaly involving the exact same particle, still turns out to be nothing more than an elaborate coincidence, it raises a quieter, more troubling question underneath the specific result itself. How would physicists ever reliably distinguish a genuine, real signal of new physics from an unusually persistent, unusually convincing statistical illusion if this anomaly, of all anomalies, cannot clear that bar? Some physicists worry this outcome would suggest current statistical methods the entire field depends on to separate real discoveries from coincidence, may need fundamental re-examination, a much larger and more disruptive project than simply ruling out one particular leptoquark or Z-prime model. Others push back against that concern, pointing out that science has always required this kind of relentless, sometimes disappointing scrutiny, and that a false alarm, however persistent and convincing it initially seemed, is simply the cost of doing careful science correctly rather than declaring victory prematurely and later being forced into an embarrassing, very public retraction. Both perspectives carry real weight, and physicists genuinely disagree about which risk matters more. What almost everyone agrees on is this: the current 4 sigma significance, however impressive it sounds, is not yet strong enough to fully settle either question. Only the additional data already flowing in from the upgraded collider can ultimately decide whether this becomes a landmark discovery, a valuable lesson in scientific caution, or something stranger still, a persistent anomaly that never quite resolves cleanly in either direction, forcing physics to sit with genuine uncertainty for years to come. Uncertainty like that is uncomfortable for a field built on precise answers, but it is also, quietly, the exact condition that has preceded nearly every major breakthrough in the history of this science. The discomfort sitting right before the picture finally comes into focus. Everything in this story now comes down to a single number sitting somewhere inside a collision dataset 3 times larger than the one that started all of this, waiting to be fully analyzed by physicists working right now, today, inside offices and computing centers scattered across the world. That number will either climb past 5 sigma, crossing the threshold that separates a persistent hint from an official discovery, or it will slide back down, joining the long, humbling list of anomalies that once looked extraordinary and quietly returned to ordinary. There is no third option left standing. The data volume involved has grown large enough, and the statistical methods sharp enough, that the coming years will almost certainly deliver a clear, final answer, ending well over a decade of careful, patient uncertainty. Consider everything riding on that single number, a potential new particle, bridging 2 families of matter that have remained permanently separate for the entire history of modern physics. A potential new force, invisible for 50 years, hiding inside the same quantum loops physicists have studied since the 1970s, without ever noticing an extra guest inside them. A potential connection to the galaxies spinning overhead right now, held together by an invisible substance nobody has ever directly touched. A potential piece of the answer explaining why anything exists at all, rather than the empty, annihilated universe basic physics originally predicted. None of that is settled yet. None of it may ever be confirmed. If the anomaly ultimately fades the way so many promising results have faded before it. But for the first time in over a decade, Physicists are not simply hoping for a lucky break or an unexpected new measurement to arrive someday. The instrument capable of finally answering this question already exists, already running, already gathering exactly the data needed to settle the matter for good. Somewhere under the border of France and Switzerland, protons are still colliding, right now at nearly the speed of light, creating B-mesons that live for less than a trillionth of a second before falling apart. Most of those decays will follow the rulebook exactly as written, just as they have for 50 unbroken years. A vanishingly small fraction, roughly 1 in every billion, will take that same rare, strange path first flagged back in 2013, the path that may or may not be bending slightly away from everything physics currently understands. Somewhere inside that flood of data, the answer is already sitting, waiting patiently to be found. 650 billion decays built this story so far. The number that finally ends it is still being counted. Whatever that number turns out to be, the search itself has already proven something worth remembering. A pattern too small to notice with the naked eye, repeated billions of times, patiently measured over more than a decade, can still shake the foundations of what an entire species believes about the universe it lives inside. The next number is coming, and when it finally arrives, it will not just close this story, it will open the next one.